lecture, we will examine the concept of the chain rule. And we start with a motivating example. And the key thing to think of with chain rule is intermediate variables. So here we have an independent variable x, a intermediate variable u, and then a dependent variable y. So here we have, in this example, y equals u cubed, and then u is a function of x. And then the question is, what is dy dx? If we change x, how does that send a change to u, which then sends a change to y? And we can actually take a look at this using some of our already established differentiation rules. So we can say dy dx is the derivative with respect to x of this function u cubed. Well, let's get a little bit creative, and let's write this as the derivative with respect to x of u times u times u. That's the same thing as u cubed. But then we can use associativity of multiplication to say this is the derivative with respect to x of, first we do u times u, and then multiply that by the third u. Now this is asking us to take the derivative of the product of two functions. We have one function here and another here. And we have our product rule. So using product rule, we can say this is, so again, by product rule, the first, which is u, times the derivative of the second. Now we're differentiating with respect to x. So the derivative of u with respect to x. Plus the second, u, times the derivative of the first, derivative with respect to x of u times u. This term here is just u squared du dx. And we have u, but now we have this derivative term that we have to handle. And again, we have product rule. So we will do the first, u, times the derivative of the second, du dx, plus the second, which is also u, times the derivative of the first, which is du dx. And now take note of what we have here. We have a u squared, but this u, when we multiply it into this expression here, we also get u squared. And there's a du dx common to each term. So this is 3 copies of the term u squared times du dx. Notice y equals u cubed. When we have 3u squared, it looks an awful lot like we did power rule on that. And that actually turns out to be exactly right. What we have here is the derivative of the dependent variable with respect to the intermediate variable. That's our dy du term. That's this. Then we have du dx. And you notice that chain rule has these two things here. That's what chain rule will be, being multiplied. And so the way you can think of this is, if you have a small change in x, that sends a change up to u via the derivative du dx. Then that resulting change in u sends a change to y via the derivative dy du. And the change is done in this multiplicative fashion. And in essence, that's chain rule. So let's look at the formal statement of the theorem. And essentially, we have just 2 different ways of writing this theorem here. So one, suppose g is differentiable at x, and f is differentiable at g of x. That's set up just so that we can plug. So look at this expression here, this composition. G is differentiable at x, so this g of x is fine. And then f is differentiable at g of x, so there's no problem with passing g into f. With this function composition, we actually have this expression here. The derivative of that composition is f prime of g of x times g prime of x. So you can think of this as when you take the derivative of this composition, you take the derivative of the outer function, leave the inner function as it is, and then multiply that by the derivative of the inner function. Equivalently, if y is equal f of u and u equals g of x, so that comes back to our picture from before where we have a dependent, an intermediate, and an independent variable, then the derivative of y with respect to x is the product of dy du du dx. We won't go through the proof of the theorem, but it's essentially this, except you have deltas. So what you end up doing is you end up looking at, say, delta y over delta x, and you can make an approximation where you have delta y over delta u times delta u over delta x, where you argue that these are small quantities, small changes, and then you end up taking a limit as delta x goes to 0 and using your limit laws, and the result is this expression here. I encourage you to look at the proof in the book. But let's look at an example. And so here, we're going to use this equation 1. Now, think about doing this problem before knowing chain rule. What you would have to do would be to FOIL this out. And when you FOIL that out, you're going to get quite a mess on your hands. It's something you'd want to do in Maple or MATLAB or some symbolic program. Alternatively, we can apply our chain rule and say h prime of x is, so here we're identifying the outer function f of u is u to the 12th. And the inner function we identify as 2x cubed plus x. That's formally how we're approaching this. What we can do, though, without even being explicit here, is say, all right, h prime of x is, take the derivative of the outer function, which is this function raised to the 12th. That's our u to the 12th. And we use power rule. 12 times that stuff to the 11th, and keep the inner function the same. So we have that 2x cubed plus x. Then multiply by the derivative of the inside. In this case, the du dx. And the derivative of the inside, we do power rule, 6x squared plus 1. We'll do several examples of this, but this is the idea. We took the derivative of the outer function, leaving the inner function alone, and then multiplied by the derivative of the inner function, which is this version 1 of the chain rule. Another example. Here, we're going to use the version dy dx is dy du times du dx. So we can calculate each of these derivatives on their own first. So to get dy du, we'll use our quotient rule And so remember, that means we have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. And notice this should simplify it because we have a u plus 1 minus u. So this becomes 1 over the quantity u plus 1 squared. We also see du dx is simply 3x squared. And we then apply chain rule using these two results. So dy dx is thus 1 over u plus 1 squared, there's our dy du, times 3x squared. And we typically want to remove the intermediate variable from our expression in the final answer. So this u, we substitute in x cubed plus 7. And there we have it. There is the rate of change of y, instantaneous rate of change of y with respect to x. Next example. Typically with these types of examples, of course, you could use reciprocal rule, but things are usually easier if we go ahead and bring all the terms up into the numerator and then apply both chain rule and power rule. So the derivative, come back to our first version, take the derivative of the outer function. So here the outer function would be, say, u to the minus 5. So you could say f of u is u to the minus 5. So when we take the derivative of this, leaving the inside alone, we have power rule, minus 5, leaving the inside alone, to the minus 6, and then times the derivative of what's inside. Inside function is x squared plus 1. We would get 2x. So here we would be saying u equals x squared plus 1. You don't have to write this. I'm just trying to write this to make sure we're explicitly seeing what we're doing. Doing the kind of story version, derivative of the outside, leave the inside alone, times the derivative of the inside, is perfectly fine when you're actually just applying your chain rule. Another example. Let's, again, rewrite this. With the inside is x to the minus 2 minus 1, all raised to the 3/2. So now we have a rational exponent. But this is fine. Our power rule works. So derivative of the outside, 3/2. 3/2 minus 1 is 1/2. Leave the inside alone. Times the derivative of the inside, which power rule on this gives us minus 2x to the minus 3. And of course, the derivative of the constant minus 1 is 0. We can clean this up a little bit. The 1/2 here and the 2 cancels. This is, of course, a square root term. So we have a minus 3. X to the minus 3 is the same thing as 1 over x cubed times the square root of 1 over x squared minus 1. Rewriting x to the minus 2 as 1 over x squared. Another example, slightly more challenging, and part of the reason to do an example like this is to practice our bookkeeping skills. But again, first, let's rewrite things in terms of powers. So that square root of 1 plus x squared we should write as 1 plus x squared to the 1/2. And now we proceed with chain rule. So let's start with what's inside the square brackets. We'll consider our inner function. Outer function will be all of that raised to the 5th. So to get our derivative, we have derivative of the outer function, leaving the inner function alone. And because sometimes these can be a bit tricky, let's just say, okay, for the chain rule, derivative of the inner function, let's just write it. So we haven't actually done that derivative yet. We want the derivative of the inside. And we can continue. So we have 5 times x squared plus quantity 1 plus x squared to the 1/2 raised to the 4th times, okay, now we can come in and do these term by term. So the derivative of x squared will be 2x. For this square root term, we will also need chain rule. So the outer function is this raised to the 1/2. So the derivative of the outer function will be 1/2 times 1 plus x squared to the minus 1/2 times the derivative of what's inside. Derivative of 1 is 0. Derivative of x squared is 2x. And if you wanted to write this a little more cleanly, we could say 5x squared plus the square root of 1 plus x squared to the 4th times 2x. Here, the 1/2 and the 2 would cancel. We have an x in the numerator, and if we bring this into the denominator, that's a square root of 1 plus x squared. So we would get plus x over root 1 plus x squared. So sometimes these questions can involve a little bit of bookkeeping, but the key thing to do with a question like this is to take your time with it. Don't skip steps. Write everything carefully. One last question we want to look at, the issue of differentiability in an example. And the example is y equals the absolute value of x. Now we know that this function is not differentiable at 0. We should have a sense for this. This function is continuous, but we have what's called a corner at x equals 0. And we can actually see this explicitly. Think of writing absolute value of x in a new kind of creative way. We can write it as the square root of x squared. So think about when this is, say, positive. If x is positive, say x is 4. Absolute value of 4 should be 4. So you would get 4 times 4 is 16. Square root of 16 is 4. What about if x is negative 4? The absolute value of minus 4 is 4. If you plugged in minus 4 here, you would get minus 4 times minus 4 is positive 16. Square root is 4. So you can see that this is another way of writing the absolute value of x. But with that, we can actually calculate its derivative. This is something we can do chain rule on. So this is x squared to the 1/2. So chain rule would say outer function is this 1/2 raised to the 1/2 power. So we would go 1/2, leave the inside alone, x squared to the minus 1/2 times the derivative of what's inside, which is 2x. Now let's simplify this. The 1/2 and the 2 cancel. We still have this x in the numerator. And in the denominator, so if we bring this x squared to the minus 1/2 term into the bottom, we would get x squared to the 1/2. Let's not simplify that. So this is x over the square root of x squared. Now, we had just said that the square root of x squared was another way to write absolute value of x. And this should ring a bell. This was the function that we had looked at. This is the sign, SIGN, of x. So think about, let's just do some examples. If x is 3, you get 3 over 3, which is 1. If x is negative 3, you get minus 3 over 3, which is minus 1. So this pulls out 1 if x is positive, minus 1 if x is negative, and it's undefined if x equals 0, because we'd have a division by 0. And we had looked at the graph of this early on in the course. So this is our f prime of x in this example. And what we're noticing is that f prime does not exist at x equals 0. Which means our original function, it does not have a derivative at x equals 0. But it is continuous at x equals 0. So we see explicitly that f of x equals the absolute value of x is not differentiable. At x equals 0, although it is continuous there. Remember that continuity, differentiability is a stronger condition than continuity. Absolute value of x, again, we say, has a corner point. At x equals 0. So when we look at this graph, it's intuitive for us to say, yeah, this doesn't make sense that there would be a tangent line, because it looks like you could draw all kinds of lines that might satisfy what we intuitively think of as a tangent line. But the idea is there is no tangent line, because there is no slope here at x equals 0. There is no natural tangent line that captures that curvature of what's happening with the function at x equals 0. And explicitly, by the machinery of differentiation, we see that if we tried to define the derivative of this function at 0, we come up with nothing. We come up that it's undefined. And so we see in this case that when you have a function like this with a corner point, we explicitly see that the derivative at that point does not exist. So that's our first treatment of chain rule. Then what's coming next will be a treatment of chain rule and rates of change. In particular, we'll do some applied examples, and we'll get a little bit more into this type of behavior. We'll actually get into the idea of what a cusp is rather than a corner.